Okay, greetings, math people. I believe this is lesson 4 of differential equations. Today we're going to look at first order separable differential equations. And I know we looked at first order separable differential equations in lesson 3, but the key today is we're going to be doing initial value problems, or IVPs. So it's not that big of a stretch from what we did in the previous lesson, but we wanted to separate the regular separable equations from the IVP problem. So let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relaxed one.
All right, so we're just going to work some examples. So we've already went through the process of solving first order separable differential equations in lesson 3. We separate, we integrate, and solve for y, basically. And now in this case, when we have this initial value or this initial condition, we'll utilize the initial condition to find the value of c. That'll really be the additional step in this particular process. And you know, there's several points where you can use the initial condition to solve for c. I generally like to do so right after I integrate. So right after I integrate, I like to plug in the initial condition and solve for c. Unless the problem dictates it would be easier to do it later. Generally, I do it right after I integrate. All right, so let's go ahead and get right into our examples. All right, so the first example, so we see we have the differential equation here. dy by dx is negative 2xy. And this guy you'll see to the side each time is the initial condition. So y of 1 equals 4. So again, this is a separable differential equation as we talked about in the previous lessons. So first we'll separate, as we talked about in the previous lesson. So first we'll separate, then we'll integrate. Now, if you notice on this separation here, you know, I can choose to move, you know, negative 2y to the other side or 2y to the other side. I have that option, but it's generally easier when you have, you know, some scalar multiple and y or some power of y, it's just to move the y by itself. So whenever I'm separating, I'm never going to take a coefficient with the y guy. I'm always just going to take the y guy by itself. So I'm never going to take a coefficient with it. And that will, in most cases, be the easiest way to do it. You know, there are, of course, you know, exceptions to the rule. Let's say, for instance, we had a rational expression here and our denominator was 3y squared. You know, in that sense, it makes sense to move the 3 with the y squared because of how it integrates. But, you know, those are different cases. But most of the time, just as I say, most of the time I'm going to find c right after I integrate. Most of the time I'm only going to move the y and not going to move any coefficient with the y. So let's go ahead and get to the separation. So the y is coming here. So this is dy over y, and that's going to equal negative 2x dx. So first we separate, then we integrate. So we can go ahead and integrate this guy. And when we do the integration, we'll get ln y, and that's going to equal negative x squared plus c. Now, again, right after I integrate, in most cases, I like to apply the initial condition and find the value of c. So what I'm going to do is I'm going to plug in 1 for x and 4 for y and solve for c. So let's do that. So this will be ln 4. 4 is a positive number, so I can just write ln 4. And 1 squared is 1, so that's a negative 1. So it's negative 1 plus c. So therefore, c would be equal to ln 4 plus 1. All right, that's the value of c. So we've used the initial condition and found the value of c. So I'm going to plug this value of c in here, and then I'm going to solve for y. So I think it would probably be advantageous to finish this out on a new sheet. So before I write it on the new sheet, just explaining what I'm going to write. I'm going to write this expression, but with this value of c plugged in. So I'm going to write ln y equals negative x squared plus ln 4 plus 1, and then go from there. So let me go ahead and write that. So ln y equals negative x squared plus ln 4 plus 1, ln 4 plus 1. All right. All right, so now let's exponentiate and solve for y. So we're going to make these guys, exponents of e. So e here and e to all of this junk here. Of course, e ln y is going to be y. Now, again, you have these exponents are being added. And so it's like each of these are being multiplied, meaning e to the negative x squared times e to the ln 4 times e to the 1. So since I'm going to do this one first, since it's just going to be a regular number. So e to the ln 4 is just 4. So I'm going to write 4. And I'm going to do this one next because that's really just a number 2. E to the power of 1 is just e. And then, of course, e to the negative x squared is e to the negative x squared. So times e to the negative x squared. I guess since these two are both base e's, I guess I can leave the sum of those exponents. So we'll write this as 1 minus, to power, the exponent is 1 minus x squared. And that solves that particular differential equation. So again, and some people, because of the way this one works out, I still prefer, even in this example, I still prefer to find c as I did right after I integrate. But some people would prefer to solve this for y first and then use the initial condition to find c. So again, there's a difference of opinion on that. It's kind of whatever you feel most comfortable doing. All right, let's look at our next example here. All right, so this looks like a fairly nice problem. And so I got dy by dx is 3y over 3x plus 5. My initial condition is that y of 0 is equal to e. So let's go ahead and do the separation. Again, I'm just going to take the y. I'm going to leave that coefficient there. So I'll have dy over y, and that'll equal 3 dx over 3x plus 5. All right. Now we integrate. This integral here is, is a little basic u substitution, if you will. So let's say I let u equal 3x plus 5. That means du would equal 3 dx. And so you can see here, this would be u and 3 dx would be du. So in essence, I'm integrating du over u, which of course is ln u. In the sake of this problem, if I substitute back what u is, it'll be ln 3x plus 5. So this integral is going to turn into ln 3x plus 5. This integral, of course, is just ln y. So we have ln y equals the ln 3x plus 5. Plus some constant. So again, I'm going to apply this initial condition and go ahead and solve for c, and I'm going to do so right now. I'm going to do so immediately. So let's go ahead and do that. So I'll plug in e for y, and ln e is simply going to be 1. And I'll plug in 0 for x, and so that would be turned into ln 5 plus c. So therefore, c would equal 1 minus ln 5. All right, so c is 1 minus ln 5. So what I'll do next on the new sheet is I'll substitute this value in for c and then go ahead and solve for y. So what I'm about to write on my new sheet is going to be ln y equals ln 3x plus 5 plus 1 minus ln 5. All right, let's find a blank sheet to write that. All right, so let's write that junk. So ln y, that's going to equal ln 3x plus 5 plus 1 minus ln 5. All right, cool. So now we're going to go ahead and exponentiate both sides. So we're going to make these exponents for our friend E. You know, all of that junk, of course. E, L, and Y. So excuse me, got a little where it's not visible. Okay, think we're better there. All right, so E, L, and Y, of course, is Y. So we'll go ahead and take it, step by step. Now, this minus sign could look very interesting if you understand the properties of exponents. These different exponents, these are being multiplied, but this guy is being divided. Now, what we can do with I can make this -1 here the exponent for this guy. So I can make this a plus and make this 5 to the power of -1, which of course is 1/5. So let me go ahead and do each part. So let me first do, let me do E, ln 3x plus 5. That'll just give me 3x plus 5. Let me now do e to the 1. That's just e. And let me do e to the ln 5 to the -1. That's just going to give me 5 to the -1, or 1/5. So and I can distribute the e if I want to. I don't want to. So this is the solution for that particular differential equation. All right. Why stop now? Let's keep going. So my next example, there we go. And so dy by dx equals y over x, and y of 2 equals 10. So let's go ahead and solve this particular guy. So let's separate and integrate. And so we'll get dy over y equals dx over x. First we separate, then we integrate. Just follow these steps and you will do great. So of course, integral of dy over y is ln y. Dx over x is ln x plus some constant. And so let's plug in our initial condition. So y is 2 when y is 10 when x is 2. So this will be ln 10, and that will equal ln 2 plus c. And so therefore c would equal ln 10 minus ln 2, which is ln 5. So c would be ln 5. And so let's plug that in for c right here. I think we have on this problem enough space to solve this one on this particular paper here. So I'm just going to write this expression with the value of c plugged in. And so I have ln y equals ln x plus ln 5. So we'll exponentiate this. We'll make these exponents of e. Of course, e, ln y, as you've seen so many times today, is y. And as you know, these are two things being multiplied. So e to the ln x times e to the ln 5. E to the ln 5 is 5. And e to the ln x is x. All right, so there's that particular guy. That guy was quite nice. So let's keep going. So I have a couple. Let's see how many more examples I have. Well, I have just 2 more examples left. All right, so we're right around 15 minutes. So we're making fairly good time. So let's get to our next problem here. And this one looks fairly elementary. So let's just go through the process. So again, I'm gonna separate and integrate. I guess I could have made these problems with a little more diversity. Each case I'm just putting dy over y. That won't be the case on my last example, but I could have spiced it up with a little more variety. So it wasn't just the last example where it's different, but we'll take what we have. So let's put the y over here. So let's dy over y, and this is going to equal 3x squared dx. Separate, integrate, ln y x cubed plus c. Here's our initial condition. Y of 0 is 3. So this will be ln 3 here, and C is going to be equal ln 3. All right, so I'm just going to plug in this value for C. So ln y will equal x cubed plus ln 3. And I think you've seen this work out enough, so we're going to exponentiate both sides, and we're going to get y equals 3 e to the power of x cubed. So I think that should make sense. It shouldn't have to be more detailed than that there. All right, so let's go ahead and do our final example. And here she is. So dy by dx is 2x minus 3 over y. The initial condition is y of 0 equals -4. So let's see what happens here. So now when we separate, since the y is at the bottom, it's going to go up here with the dy. So it won't be dy over y for once. It'll be y dy, and that will equal 2x minus 3 dx. All right, let's integrate. And if we integrate y, we'll get y squared over 2. And if we integrate this, we'll get x squared minus 3x plus some constant. All right, so let's apply our initial condition, plug in 0 for x and -4 for y. If we plug in 0 for x, all this will cancel. And so we'll just be left with C. And if we plug in -4 for y, that'll be 16 over 2, which will equal 8. So C equals 8. So going back to this guy, I'm just going to write this guy with this value plugged in for C. So y squared over 2. So y squared over 2 equals x squared minus 3x plus 8. Let's multiply by 2. So y squared equals 2x squared minus 6x plus 16. And let's take the square root. 2x squared minus 6x plus 16. Now, there's one thing to be careful about on this problem. Now, we took this square root here, but there's two branches to the square root. There's a positive branch and a negative branch. And sometimes what you'll see, and sometimes for our AP calculus people, you'll see multiple choice questions where a problem like this, one answer would be the square root of 2x squared minus 6x plus 16. And the other answer choice will be negative square root of 2x squared minus 6x plus 16. So I've seen this before. And the deal is you got to utilize your initial condition to understand what branch you're using. Now, if it said y of 0 equals +4, this will be my answer. But the fact that it says y of 0 equals -4, I need that negative sign there. All right. All right, so ladies and gentlemen, that concludes lesson number 4 of differential equations, first order separable differential equations with initial conditions, or IVP, first order separable differential equations. We hope you got something from this, and we will see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe-to-toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.